In this video, we'll continue our discussion of section 7.4. We're going to do the transform of an integral. So we're going to work on equations that have integrals in the equations to solve for functions that are in the integrals. Okay, so we have it's called a Volterra integral equation. The convolution theorem makes these types of problems much easier, and you'll see in the middle of it. Remember, the whole point of the convolution and introducing it in this course is because once I have a convolution, then the Laplace of a convolution is pretty straightforward. Okay, so they give us a new theorem here, and I just want to show you how they came up with it. If we did the convolution of one, let's flip it, of one f of t convoluted with 1, then that's going to be 0 to t. And then I have f of tau, and then the g of t in this case is a 1. So g of t minus tau, minus tau is also 1. It doesn't change. So we just get d tau. Okay. And so if that's the case, then taking the Laplace of that, Laplace of f of t and 1, well, that means that we just take the Laplace of each one. So I get f of s times 1 over s. Well, then that's how they got their formula from there. All right, so we have f of s over s. Well, you're going to use that in a moment also to come up with some more formulas. So let's give it a go and try it here. All right, so they gave us solve f of t equals 2t minus 4 times that integral. So we're going to use Laplace. So I'm going to take the Laplace of f of t, and then the Laplace of everything on this side. Tau, f of t minus tau. So what makes this kind of tough is that we're solving for f of t, right? We got to find that function. Not only do they define the function f of t equals, but f of t is also defined with the integral of itself, which is kind of weird. All right, so I get f of s on the left. 2t is just going to be 2 over s squared. Okay, and then minus, and this is going to be 4. And then this is, if you'll look here, that's the convolution of sine and f of t. So this is actually the Laplace of sine of little t convoluted with f of t. That whole integral there. All right, so f of s then is equal to 2 over s squared minus 4. And then I just split them and multiply them. So sine of t is going to be 1 over s squared plus 1 times f of s. Right? I'm going to get rid of since we have a fraction, let's go ahead and I'm going to get rid of it by multiplying everything by the two denominators multiplied together. It's going to make things kind of work out simpler in the end. Meaning, okay, so I get f of s times, I'm going to have s squared times s squared plus 1. And then I'm going to have 2 times s squared plus 1 minus 4 times s squared f of s. Seemed like it was going to be a whole lot, but a lot of things cancel that will make that a little nicer and not so hard to calculate. All right, so I see that I have two f of s terms there and there. So I'm going to go ahead and bring one side to the other. So I'm going to have a capital F of s times s squared plus 1, and then plus 4s squared. Adding it to the other side, and then I got 2 over s squared plus 1. Right? I'm going to rewrite this. This is f of s times, and this is going to be s squared times s squared plus 1 plus 4. I factored out s squared of both of those terms. If you look here, if I multiply there and then there, I get back to where I was. If you can see this, this makes this a little nicer. I get f of s times s squared times s squared plus 5. And 2 times s squared plus 1. And then if I divide now, I get f of s equals 2, and I'm going to go ahead and multiply this out, 2 squared plus 2 over s squared times s squared plus 5. All right, everything has an s squared. We're going to have to do partial fraction decomposition. I'm going to do it over here since I have the room here. But the thing is, this one's kind of weird. Since s squared is everywhere, you could think about taking this and letting s squared be u, figuring it all out, and then just replacing it again, avoiding the square. So what I mean, what we can do instead of having to do like a(s) plus b for each term and stuff like that, or a over s, a over b, or b over s squared, and then have to do the s squared plus 5 separate with that, but you have a c s plus, it gets way complicated. So I'll show you what we could do instead. Since s squared is the only one, mathematically, I could just replace it with a u, which means all I would have to do is an a over s squared, and then a b over s squared plus 5. Think about if it were u, that's what we would do, right? I know it's weird because you're used to putting an as plus b, or a over s, b over s squared, and then over this one, you would have to do like a cs plus d on top, but I don't have to do that since they're all s squared. Okay, I hope that makes sense. 2s squared plus 2 equals, I'm going to multiply by the denominators. I get a times s squared plus 5, and then b times s squared. Oof, a lot of work. Okay, so if I let s equals 0, I get 2 equals 5a, which tells me a is 2/5. If I do s equals 1, I get 4 equals, I know a is 2 over 5 times 6 plus b. If I do all that math, I get b is 8 over 5. You could try that if you'd like. So what that means then is that capital F of s is equal to 2/5 over s squared plus 8/5 over s squared plus 5. All right, that first one, we could take the inverse Laplace, not a big deal. The second one, we need to do a little bit of work. You can see s squared plus 5. There is no s on top, so that means we're trying to get a sign. So let's rewrite it. So capital F of s, nothing changes up front. All right, and then I'm going to start rewriting this differently. We're going to do a fraction times, and then this big fraction. I'm going to do an s squared plus the square root of 5 squared. Remember, I had to have an s squared plus k squared, so I'm forcing what k is, and I'm going to put a square root of 5 here, and the square root out of 5 here has to cancel, and then I have to retain that 8/5. I'm just going to put the 8/5 there. Okay, so now that's actually set up. So f of t then is 2 over 5t plus, and then I'm going to put this fraction together. This is 8 over 5 root 5, and this is going to be sine root 5t. And there is our solution. Okay, we're going to do another application in the same video and go ahead and knock them out. So this is what I was talking about in a previous video, that we mainly use convolution in this context as a shortcut, because it took this integral right there and turned it into this nice pretty one that we could just multiply. Works out in our favor. All right, let's do a series circuit problem. That's our next one. So I'll let you read through that. What we get from this is we have a differential equation. and my pronunciation for things aren't the greatest, so I'll just leave it there. Um, integral differential. I don't know. I just feel like I mumble through things. Okay, so they have I of t is the current, L, R, C are constants, and it follows that that the current of circuit. There's a figure in your book if you'd like to go take a look at that. Is governed by this equation. They give us that. What we're going to do is just plug things in and work it out. I don't really need to know much about electricity or why this is working and why these laws work out. They gave me the equation. I'm going to plug it in and solve it. All right, so L, I'm going to plug in everything. So L is the 0.005. Let me zoom in so I don't write so big. 0.005 times di dt plus I of t, R was 1, plus 1 over 0.02, integral from 0 to t of I of tau d tau, and this equals 100 times t minus 1 times the heaviside function of t minus 1. When I was working my notes, I wrote that problem down 3 times wrong. Wrote it wrong 3 times, and this is was the final one. So here we go. I'm going to get rid of that 0.005 by dividing by it. It's going to make numbers big, but I would rather have a constant out front. So this is going to be 200. We're actually multiplying by 200. 200 IT. Okay, and then this works out to be a 10,000. 0 to t, I of tau, d tau. And then dividing on this side is going to produce a 20,000. And then nothing changes inside there. Okay. So now we can go ahead and take our Laplace. I'm not going to write the L for this since this is so long. I'm just going to go ahead and take it. I'm going to put up here that the Laplace of I of t is going to be capital I of s, like that. All right, so we got to be careful here. I'm going to get s times capital I of s minus I of 0 plus 200 big I of s. And then it's going to be the Laplace of this. So I'm just going to put 10,000 and then the Laplace of 0 to t I of tau d tau. We'll deal with that in a moment. All right, and this equals then, if I'm going to go ahead and do the Laplace of this side. I'm going to get a 20,000. The Laplace of t is 1 over s squared. All right, and then what we're going to use here is we have t minus 1 and ut minus 1. So remember, this is treating this as, I'll have a negative, but that's just a t. And then I'm going to flip it over. So it's just going to become, I get the e. Let me write the rule down. I feel like I'm messing this up. F of t minus 1, u of t minus 1, Laplace, right? What this meant was that I had a e to the negative. Let's grab this correctly. I always feel like I'm going to get it wrong, and I don't want to do a middle of a video wrong. So we have that. Actually, I flipped like literally right to it. No, I was right. Okay, negative AS, capital F of S. That's what the rule we're about to use. So it's going to be e to the negative t, and then our function in this case, it has to have the t minus 1, so it's just a t. So it's 1 over s squared. I want you to go ahead and look at the rule for that. This f of t in this case, this is t minus 1. So it would be a t. Like if f was t, right? Then f of t minus 1 is t minus 1. So when I did this part, this was just the Laplace of t. I hope that makes sense. Okay. So I'm going to erase all that's here. All right, we can go ahead and put things together. I of 0 was 0, thankfully. I'm going to put, okay, we need to work on, I have I of S here plus 200 I of S, and then we got to work on this part. This is, it's just a function. We have that rule for this. This is going to be 10,000 because that was the constant out front. And then remember, we get capital I of S, F of S, and then it's over S. That was the rule. And then over here, things are the same. I don't know, does it benefit us later to put those together? No, it does. Oh, they're both over S squared, so we might as well. This is over S squared, 1 minus e to the negative t. Yeah, that doesn't hurt anything. Okay, I have I to the S on everything in the left. That's kind of nice. So I'm going to get S plus 200 plus 10,000 over S equals, and then nothing changes over here. Maybe I'll go ahead and put the S over the 20,000. Okay, I think we should get a common fraction on the left if we can. So the common denominator here is just an S. So I'm going to multiply everything by S and then put it over S. So I got S squared plus 200S and then plus 10,000 because it had an S on the bottom and that was the point it canceled it. Or it didn't cancel it, but we had to multiply everything by S to get that common denominator of S. Right, 20,000 over S times 1 minus e to the negative t. Things have worked out in our favor. Actually, we should do one more thing. Capital I of S. And then the thing here is that top actually factors to S. Let me fix my S so if there's a 5, we don't get it confused. S plus 100 squared over S. And then nothing changes over here. Okay. Now I'm going to solve for I of S by just multiplying by the reciprocal. So I of S equals, do you see that the S's are going to cancel? And I'm going to get 20,000 over S plus 100 squared times 1 minus e to the negative t. All right. I'm going to leave the 1 minus e to the negative t alone. And we want to do a fraction decomposition. I think we're missing an S somewhere. And it happened a while back. It was right here. Some of you guys have, like I always said, probably screaming at me the whole time. So we have an S right here. It was right here that we lost. I'm glad we found it. Okay, so we have that. I'm going to do a fraction decomposition. 20,000 over S times S plus 100 squared is going to be A over S, B over S plus 100, and then C over that squared. All right. If I follow out the fraction decomposition, I multiply, I get 20,000 equals A times S plus 100 squared. I get B S times S plus 100, and then a CS. All right, this works out pretty quick. S being negative 100 will be a 20,000 equals negative 100C. That means that C is negative 200. We could do S0 as well. That's 20,000 equals, everything goes away except for A is 100 squared. So I get 100 squared is 10,000 A. That means that A is 2. And then the last thing, S is 1. I get 20,000 equals, and I'm going to plug things in. I get 2, because A is 2, times 101 squared plus b times 101 minus 200. Okay, I'm going to go ahead and give you what b is. B is -2. Okay, so now I'm going to rewrite I of s. I of s now is 2 over s plus -2 over s plus 100. C is -200 over s plus 100 squared. And all this is times 1 minus e to the negative s, if I remember. Let's go back. Had a t. It should be an s. Where did it change? Oh. Ooh, big mistake the whole time. That should be s. Forgive me, guys. I should be following my notes. Easy fix, though. Negative s. Negative s. It should have been a red flag the whole time because remember, Laplace takes us to s, and then we take it back. There we go. My notes have negative s. My brain did not. There we go. But I'm glad that was an easy fix. Didn't require us reworking the whole thing or erasing a lot. All right. So what I'm going to do now, this thing, the three things in the parentheses here, those are pretty easy to take our inverse Laplace. But we got this weird term connected to it. But notice it's just 1 and then minus the e. So what we're going to do is I'm going to rewrite this thing. And forgive me, I'm going to copy and paste here. But I'm just going to get the function and then minus e to the negative s of the same thing. Let me shrink this up. And that's just times the e. That e there is easy to deal with because remember that when I have an e like that, negative s, going backwards, that's just a unit step function, right? And then we treat it, let's go through it. So then I of t is going to just be a 2, and then a minus 2 e to the negative 100 t. Okay, and then what happens here, if I have the s plus 100, what happens here is this is kind of like the derivative thing. I get minus 200 t e to the negative 100 t, right? What's happening here, all right? It's kind of confusing, but if we were to take the Laplace of this thing, the negative e to the negative 100 part tells me to do the s, like I'm going to now do the Laplace of negative 200 t, and then remember we change s to s minus 100, or plus 100 rather. It's the difference, this opposite there. This would be negative 200 over squared normally with t, but it's going to be s plus 100 squared. I hope that makes sense. So anytime you see the s plus 100 inside of a square or something like that, that's what we're thinking. Now, what's great about this problem, I guess I could leave all that. I changed it already. It's plus 100 squared. Okay. Now, what's great is we get that same exact thing. So I'm going to do a minus, and then I'm just going to put that same thing in here. Oh, I want you to copy. I don't know why it's not letting me do it. Oh, well, I'll write it again. Okay, I got 2 minus 2 e to the negative 100 t minus 200 t e to the negative 100 t. And then I just times the whole thing by the unit function, unit step function u t minus 1. That's what this produced. Okay, and there is our solution. Ugh, right? It gets pretty complicated here, but we have the tools to work through it. Just don't get lost in the sauce, right? Go slow, write big, make sure you're checking things.